Yes, good morning and welcome everyone to this webinar. I am Sanna Hiltunen, Project Planning Officer at Oulu University of Applied Sciences, and I will be hosting you through this webinar today. It's my first, so let's hope that everything goes smoothly. This webinar is recorded and the recording will be made available later online at SMARTrenew project website. And I would ask that all participants in the audience will keep their mics muted during presentations and their videos turned off. If you have any questions during the presentations, please send them to us through chat, and there's time reserved after each presentation for questions and discussion. Now let's see about the timetable we have. Yes, we're going to have a very interesting 2 hours ahead of us. We did change our schedule from the original a little bit. So starting at 8:50, instead of Fingrid's presentation, Jonna Kannosto from Merus Power will tell us how battery energy storages support wind energy in electricity network and boost its competitiveness in the electricity markets. And then after a little break, Tuomas Rauhala from Fingrid will join us and give us a wider perspective on Finnish power network balance and other new operators on the electricity markets. Then before closing, Heikki Kurki will present the brand new Oulu University of Applied Sciences hybrid laboratory from the electricity and automation point of view, and what cooperation possibilities might be in store there. Before we go further ahead, I'd like to shortly introduce to you the SMARTrenew project that this webinar too is part of. So SMARTrenew, smarter renewable energy and heating management for Arctic and northern rural territories. It's an Interreg NPA funded project that aims to reduce energy poverty and increase energy security in the northern periphery and Arctic area, the NPA area, through shared and increased knowledge and implementations on smart renewable energy and energy storage solutions. It's a 3-year project that started in October 2018. It has a budget of approximately 1.6 million euros, and it's led by Dr. Nick Timmons from the Letterkenny Institute of Technology in Ireland. Other partners are from Ireland as well, Donegal County Council, from Northern Ireland, Derry and Strabane District Council, from Norway, NORUT, the Northern Research Institute Narvik ES, and from Iceland, Heat Research and Development, and the energy agency Orkusetur. Environmental agency from Faroe Islands, and of course from Finland, Oulu University of Applied Sciences. You can find more information on the project from our website, smartrenew.interreg-npa.eu. And the project is on social media platforms as well, for example, on Twitter and LinkedIn. Now, in this project, the partners are implementing different pilot cases to test and evaluate different solutions to increase local energy security in green and more sustainable ways. Let's take a little peek on what kind of pilots we have ongoing. So let's start with the lead partner, Letterkenny Institute of Technology, Ireland. They are planning for solar energies and storage to drive their electric car chargers in their campus car park. They are slow charges, which will suit staff who park their cars there all day. It will be packed up with connection to the grid. It incorporates renewables and storage, promotes green electric vehicle charging and electric vehicle charger installations, which are currently a bit slow in Ireland. Next, from Ireland as well, is Donegal County Council. They have this Milford Public Services Centre and Library. It's a public building built in 2003, and it's heated. Its water and space heating is done with two oil-fired boilers, and their pilot is about removing the oil-fired boilers and installing photovoltaic panels, air-to-water heat pumps, batteries for smart storage, and adding some extra insulation to get better energy rating for the building, thermal energy savings, and getting rid of the dependency on heating oil. Then the Derry and Strabane District Council from Northern Ireland. They have actually two cases, at least. There's this heat boss control system integration at Guildhall and Harbour House, so two buildings that they are integrating with more efficient heating systems to reduce fuel consumption, carbon emissions, and heating costs. Then their other case is optimizing solar photovoltaic, battery storage, and heat pump technology for this Lincoln Courts Community Center building. And they plan to get reduction in energy costs, CO2 emissions, and fossil fuel energy consumption. That's it in short. Then we move to Iceland, where the energy agency Orkusetur and Heat Research and Development are piloting this case called Grimsey Renewable. Grimsey is the last diesel economy in the municipality of Akureyri in Iceland. And they want to integrate renewables with the existing diesel engine dominated system. Those renewables include solar panels and 100 kilowatt wind turbine, for example. And load control would be gained through heat storage, storing heat in hot water, used also to heat indoor spaces. And they plan to benefit in getting renewable and local energy and smaller carbon footprint, getting rid of some of that diesel use. Next in line, unvuorovistuvan the Environmental Agency of Faroe Islands are testing heat storage in the Faroe Islands. It's a remote location in the middle of the Northeast Atlantic, and over 90% of the energy use is still from imported oil. But the society is being and will be electrified, and wind parks are being developed, and energy storage is important in that point of view as well, because the energy storages are needed for the fluctuating renewable energy. Around 20% of their total energy is used for space heating, and ground source heat pumps are lately replacing oil heating, oil burners, and they are testing storing heat in the boreholes of the heat pumps. Then we reach Norway, where are two cases. This Element Nor, which is a case in smart approach for carbon footprint reduction. Element Nor is a small or medium-sized company that makes prefabricated concrete products. And they wish to use solar energy to reduce the need for fossil fuels in the production process, and also energy storage and smarter energy management to get the carbon footprint smaller. Their other case is off-grid households in the far north. They have two families at different stages of implementing off-grid living, and they plan to have sensor setups to gather weather data, and then based on that data and simulations to give recommendations for adjustments and next steps, how to get everything just so in the off-grid living. It works as a showcase of the possibilities of being off-grid so far in north. It's in the Lofots, so very far in north with the polar night and everything. And then we arrive here in Oulu University of Applied Sciences and Finland. We are piloting with Energy and Water Cooperative EVO in Kuusamo, smart heat storage and district heating. Energy and Water Cooperative EVO takes care of district heating in Kuusamo area, and they are investing in a heat storage tank to help even the loads and aid in meeting the peak demand in district heating. The aim is also to reduce use of fossil fuels. The heat for the district heating is mainly produced at the local CHP plant, which uses wood-based biomass as fuel. But when the peaks in demand are very high, sometimes the auxiliary oil burning heat-only boilers are needed too. And getting to cut some of that oil burning and fossil fuel would mean less emissions and also savings from fuel costs as well. There's also a possibility for increased electricity sales, as the heat storage can be a consumer for the CHP when the electricity market prices are high and it's profitable to make electricity or produce electricity. And now the Oulu University of Applied Sciences comes in with to the optimizing of the use of the heat storage, and we're involved in bringing in the smart component. We are producing a calculator. Our project worker Lauri Pelkonen is working with this currently, and the idea is that the calculator could estimate the upcoming energy production demand based on weather forecasts and forecasts on the outside temperature for the next day. And then based on the calculated energy production demand and also the forecast of electricity prices for the next day, the calculator could give indicators on when to charge or discharge the heat storage. So this is something that we are doing here, and with the Evo in Kuusamo. Are there any questions for right now? Any questions in the? No questions in the chat either. So these pilots are currently ongoing, and we will report on their success and results as they progress, and with more detail as the SMARTrenew project nears its ending. According to our original schedule, SMARTrenew project would end by the end of September 2021, but there will probably be extension due to COVID-19 related delays, which is the case for probably many projects these days, unfortunately. But so at least a year, maybe a bit longer to go still. If you'd like to know more or have ideas for cooperation, don't hesitate to contact. There's my contact information right there. And if you'd like to know something or more on any specific pilot from our partners, I'd be glad to put you in touch with the person who can answer your questions the best. If there's no questions at this moment, I thank you. And we are minutes ahead of the schedule, but let's hear about wind energy and battery energy storages from Jonna Kannosto next. Jonna, the stage is yours.
Thank you, Sanna, and thank you for your presentation. Sounds you have a very interesting projects going on.
Yeah, lots going on. A lot is going on, yes.
Okay, so my name is Jonna Kannosto. I'm a marketing manager at the Merus Power. Today I'm going to talk about the energy storage and how it can support the wind energy in the electricity network, and also how the energy storages can increase the competitiveness of the wind power in the electricity market. I will shortly introduce our company and then tell a little bit more about the wind power in Finland at the moment. and then we go to the benefits of combination of wind power and energy storages. And the frequency response service is the important part of that. So I'm going to talk about the FFR and FCRN markets. And then today we are going to also hear, I guess, more about these different frequency response services from Fingrid. Merus Power is a global cleantech company. We are located in a city of Nokia in Finland. We design, manufacture and sell energy storages and also different power quality solutions. We can help our customers to increase the productivity, but also save energy and nature. The good thing is that they can also increase the revenue at the same time. We have a very long experience to work with different customers around the world in different applications, like in industry, utility and infrastructure sectors, but also with renewable energy. We have customers in 36 different countries, if I have keep up our records. Then about the wind power in Finland. The market growth has started in Finland about 2012, and this is a little bit later than in Europe in general, where the growth started already before 2010. At the moment we have, or end of the year 2019, we had 2,284 megawatt and about 754 turbines installed. And those was producing 5.9 terawatt hour electricity. And this was covering about the 7% of the consumption in the Finland. About 70% of wind production is owned by Finnish companies, and the rest of the 30% is for different European companies. And the interest of investing to Finland is growing. And it's because of the profitability of the wind power is increasing. And one thing I will introduce today is also how the battery energy storage can support the profitability, but also the one important thing why the profitability is increasing and why the investments are more interesting is that the large companies, for example, like Google, they have made a contract of buying 190 megawatt of wind power capacity lately. So these kind of contracts help the investors, and the market will grow even faster. The wind turbines are not distributed evenly to the Finland. Almost 40% of all wind turbines are located in northern Ostrobothnia, around the Oulu area. But the potential of the increased wind power capacity in Finland is quite large. So we have a lot of free space, a lot of forests, and then we have a very long coastline also. All these will help the wind power to grow in Finland, and probably the main thing is that we have a lot of wind here. There are different estimations how the market will grow. One estimation is that in 2030, the annual production would be already 30 terawatt hour, and it would be 30% of the consumption in Finland. And in general, Finland has a great potential to be even an exporting country for wind power. And it would be very nice to see in the future. So then we are going to talk about how we can support wind power. First, I will introduce how the wind power will work in an electricity market in general. So first, the wind power stations, they need a weathercast. When they know how much there will be a wind, they can estimate the production, and they will sell it in day before market, in L-spot market. And there will be also a new for the weathercast. And then 1 hour before, they can they can sell or buy the difference between the previous estimation and the new estimation in LBAS market. But even all these estimations, the real production is not necessarily what has been estimated. If you look the picture in the middle and in down, you can see the orange line. It's a day ahead estimation of the production, and in the blue line is the forecast 1 hour before, and then in a black line you can see the real production. And this is free data from Fingrid's webpage, and only one example how these differentiate. During the nighttime, the estimation is quite close, but then in this case, in the daytime, there is difference between the estimations and the real production. And more we have green energy in our power grid, the more uncertainty we will get. And this needs support from the grid. And for example, the battery energy storages can support this, support these differences. And for example, Meru's ESS energy storage, it supports the power grid, but also the wind power stations. And now when we know that there are differences, so what it means in the electric grid, if you look the right-hand side, the picture, the generation, there are different power generation methods like green energy, solar and wind power. But then there is also kind of base load generators like nuclear power plants or coal plants. The generation need to be balanced. It need to be equal with the load, so how the electricity is consumed. And if there is imbalance, it can see in the frequency. And with the energy storages, we are able to help this imbalance. If these generators are producing more electricity than the loads are using, the frequency will increase. And if the loads are using more electricity than the generators are producing, the frequency will decrease. So the important here is the frequency of the electricity. And that's why there are frequency response services. And the faster we are able to react that frequency drop or increase, the better it is. Now we have a new response market, FFR market, which is very fast. The response time is about 1 second. And here in the table, you can see also other response service functions. And in my examples, we are going to talk today about the FFR market and FCRN markets, where the response time is some seconds. This new FFR market was defined by Enzo E, and it was started in May this year in Finland and in Nordics. This has a very fast reaction time, and in the table in the right-hand side, you can see the activation times, which are going from 0.7 seconds up to the 1.3 seconds. And then there's the activation frequency, which means that, for example, if the frequency will drop to the 49.7 Hertz, there's a 1.3 second time to react to that drop. And the duration time to support the grid in this case is minimum the 5 seconds. Meru's energy storage ESS reaction time is 20 milliseconds, meaning 0.02 seconds. So it can react very fast. So it can fulfill this highest class in the bottom where the reaction time is 0.7. And the activation limit is 49.5 Hertz. So this FFR market is an hourly-based market. The price is defined by bidding each hour. And when we have analyzed the data from the Fingrid's net webpage, the average price from the last summer was 75.6 euros per megawatt, and this is a very high price. The combination of energy storage and the wind farm can get the higher profitability from the electricity market. So the charging of the energy storage can be done with the excess power, like we was seeing from the graph 2 slides ago. Sometimes wind power can produce more electricity than estimated. For example, in these cases, the batteries can be charged, and then the power can be used to support the grid. The reaction time with the Meru's ESS is extremely fast, and in this higher class where the reaction time is 0.7 seconds, and if it would have been in this market, what you have seen in this picture, with the 6 megawatt energy storage, the revenue for the wind farm would have been 75,000 euros from this summer. So it can increase the revenue. Now, if the same energy storage would be in an FCRN market, where the reaction time is some seconds, the average price from this year has been for that market 13.2 euros per megawatt, so the price is a little bit lower. And if the wind farm would use this ESS in the FCRN market, the estimated income from this year would have been 600 and almost 70,000 euros. And for example, with this price, the investment payback time would be 5 to 6 years, and these kind of energy storages can be used for 10 to 20 years. Of course, depending on the batteries, and maybe the batteries need to be changed, but it's just a part of the energy storages. So with the energy storages, the wind farm get more revenue and they have higher profitability in the electricity market. So how this look in a graph? So here we can see the battery energy storage and the wind farm. They are both producing the electricity to the grid. But the battery energy storage can also, it can when it's discharging, it can feed the energy to the network, but when it's charging, it can take the electricity from the network. So if the frequency goes higher, it can charge to get the frequency back to the normal, or if the frequency is getting lower, it can feed the electricity to the network. There's a measurement points in a grid so that the energy storage will see when the frequencies start to decrease or increase to be able to react in that difference. And also it can communicate with the wind farm itself, so they can discuss, and when the wind farm is producing also electricity to the batteries. So the wind power can produce unbalanced to the network grid, but with the energy storage, the wind power can support this difference, this frequency difference, what can be seen in the electric grids. And at the same time, they get the more revenue from the electricity market and increase the profitability of the wind power. But this is not all. So Meru's ESS energy storages, they can also support the wind power stations. They can measure and control the total power, and they enable the black start for the wind farms, but also they can filter the harmonics and help to meet the grid requirements. Sometimes the turbines can give some harmonics to the grid, and because the reaction time of the energy storage is extremely fast, so it's inside the one frequency, so that's why it can also kind of minimize the harmonics. But here we have been talking about how the energy storages can support the wind farm, but this is the same case for all green energy. So with the battery storage can support also the hydropower and solar power, so all the green energy in the network. For example, for the solar panels, the full benefits would be, for example, when there's basically no limitations how many solar panels you can install, because you can produce more electricity with the solar panels than you are using. Extra power can be stored to the battery energy storage, and then it can be used when there is a consumption peaks. And because of the power quality ability, it can allow the very easy integration to the network, because this energy storage can take care of the supporting kind of the problems in the power quality. And when this battery energy storage also is part of the response services, also the revenue can increase and shorten the payback period of these installations. With the hydropower, the benefits are even higher. So in hydropower, when hydropower station is part of the FCR markets, the change in the production is made by turbine blades. They need to move. So the distance movements can be reduced for 52% approximately, and this number of movements are reduced by 82%. So all these both of these means that this expected lifetime is more than a double. And this is a great benefit for hydropowers. The service for the hydropower stations is extremely expensive. And when the lifetime can be doubled, for example, it means a lot. And when the battery energy storage help the hydropower station to be part of the FCR, for example, end market, it can increase the revenue and reduce, of course, the maintenance costs. This was all what I was going to say today about how the battery energy storage can support the green energy. And I would be very happy to take all your questions, what you might have.
Sami Martinmäki is asking, is the wind farm plus battery energy storage working at the moment in Finland?
We have a Nordic largest battery energy storage in E, and it's 6 megawatt battery energy storage, and it's accepted to so it has fulfilled the Fingrid's test just some time ago. So it's kind of in operation.
Okay. And another question in the chat from Ensa Ikonen, what about hydropower? So hydropower plus battery energy storage is working in Finland currently?
No, this kind of combination we don't have in Finland at the moment, but we have been using a lot of data from the large Finnish company to estimate all these movements and payback times and so on. So there's a lot of data what we have been using, and that data is from Finland. But how would I say? It doesn't, in a battery energy storage point of view, it doesn't change too much when we are changing the generation method.
Okay. For me, at least, there was a lot, so much new information that I probably have to go
adapt
back
it for a while.
Yeah, yeah, and then go back and watch the recording and learn from it. But
yeah, of course, I'm happy to take the questions afterward also, so you can find my contact information from Merus Power's webpage.
Yeah, there's one more question from Antti Yrjölä. What is the capacity of the e-battery storage facility?
It's a 6 megawatt and about I cannot remember, but it was about 6 megawatt hours also about. There's a tree. It's a very large battery energy storage for the FCR market, and basically what there is 6 different these kind of containers what you have seen in the presentation. So 3 of those is basically kind of head of the station, and then there's 3 different containers just for batteries, and they are installed in a large building so that the snow cannot cover the storages.
Okay. I think I'm gonna steal the sharing away from you. if you don't.
I don't mind.
Sorry. And now, unless there are any more questions at this moment, I think we're going to have a little break. And then we'll get back at 9:30 and we'll continue with Tuomas Rauhala from Fingrid. So see you all in a bit. So it's almost 30 minutes past 9. I hope you can hear me all right. And I think we have Tuomas Rauhala from Fingrid online. Welcome, Tuomas.
Okay, another go. So pleasure to be with you. I hope you hear me this time well.
Yes, now we can hear you.
Oh, that's much better.
Yeah.
Right. So how was the morning? How was the first session? Are you ready to go?
Yes, we are ready to go, and it's been very informative. Jonna told us about the wind energy and battery storages, and I learned so much new things that my head is exploding right now. And I suppose it's only getting worse worse soon, but yes, we're ready to go forward. So stage is yours.
Okay, very good. I hope you can hear see also the presentation now on the shared screen. I presume so, because there are no immediate objections. So, well, good morning, everyone. I am Tuomas Rauhala. At the moment, I'm working as manager of our Flexibility Market Innovations unit at Fingrid. Briefly, my background, I've been with Fingrid for quite a long time, roughly 20 years, depending the way you calculate it. I started, well, as a summer trainee, then spent some 7 years, mainly dealing with system planning, system technical performance, wide variety of different kind of issues, starting from power system engineering to the power quality, HVDC systems, grid connection requirements for the power plants. And then I shifted towards the asset management. I was there with our investments and maintenance for 5 years. And just recently, actually half a year ago, I joined our market department. And especially, of course, thanks to my new duties, I've been concentrating really on the new flexibility, how we can channel the flexibility provided by the new energy resources in future to the market, so that the new flexibility will provide as much added value as possible, not only for the owner of the assets, but also for the network operators. And okay, yes, I have also some academic hobbies. I would say I'm been serving as a docent at Tampere University of Technology on a field of distributed resources in transmission systems since late 2017, I think. So that's briefly regarding my background. And again, because of this interest, because of my duties nowadays, I took a liberty to change a bit of the title of the presentation, especially after hearing a bit more about this research project, and as seeing also some glimpse of the other topics that are being covered during this webinar. But nevertheless, I will briefly, before really entering to the topic, being the need for new flexibility and especially the grid owner's perspective, I thought that I should say a few words about the Fingrid. We are the transmission system operator, so essentially we own and operate the high voltage transmission network in Finland. all the highest voltage levels, and half roughly of the sub-transmission system being 110 kV in Finland. And our target is to really secure reliable electricity for the customers as well as the nation, and at the same time shaping the clean, market-oriented power system of the future. A bit of the company we own and of course operate as well, roughly 15,000 kilometers of power lines. We have roughly 400 employees. And the electricity which was transmitted through our grid back in 2018 was roughly roughly 74% of the total transmission volume in Finland. And what else I could say? We participate number of the benchmark surveys between the transmission system operators. And essentially, I would say year after year, we are among the best ones, especially considering the reliability of the grid as well as the management of the maintenance, the way we do the assets management. And one of the key figures, obviously, for any transmission system operator is the reliability of the grid. And the figure which we have is essentially 6 times 9, 99.9999, and this is actually pretty much the focus of, I would say, also this presentation, because as you all know, because of this ongoing transition in the energy systems, through the heavily increasing integration of intermittent renewable generation, that essentially presents a huge challenge for any electricity system operator or any player in this industry. And especially from our perspective, as we are the owner and operator of the critical infrastructure in Finland, one of the key targets for us is, of course, to maintain the high reliability on the grid. And for that purpose, of course, we think that the new energy resources, they will also play a key role, and we need to be able to take full advantage of their flexibility potential to ensure that also in future the reliability figure is at the same brilliant level as it has been during the last decade and so. But then the case for the new flexibility, I thought that I should actually start with kind of an introduction, what is meant by flexibility and why there is the need for new flexibility, and of course in a wider perspective, what is being referred as the flexibility and the flexibility markets, which obviously are as well covered in the presentation. So if we start from basics, for the transmission system operator, TSO, the need for flexibility, they essentially come from three, I would say, main tasks of ours. We need to maintain the balance between the generation and consumption all the time, 24/7. And essentially for those purposes, we have the balancing power markets, the balancing power resources. Then, of course, there is the target to maintain the normal system frequency. We need to maintain that one during all kinds of operational situations, including the network disturbances. And for that purpose, we have the frequency reserve market. And there is various of frequency reserve products, as you heard already during the morning presentation. Additionally, we have a need to ensure the adequacy of the transmission capability of the network during each and every operational situation, including the disturbances. So, well, what this implies, it says that each of our network components, they have a certain capability to tolerate current flow through the components. And when the power balance in the system, when the generation consumption varies in the system, we have to all the time ensure that none of the components becomes overstressed. And the congestion management is something we do essentially not all the time, but on regular basis, and especially during the network disturbances. If we lose a single network component, we rather often have to do some, let's say, rescheduling of the generation, so to ensure that none of the remaining components becomes overstressed. And the congestion management is nowadays done mainly using this balancing power markets resources. In some extent also, let's say, offers from the intraday markets. But the reason why I really wanted to take a bit more time with this congestion management issue, and this is actually one of the key factors where we see a significant increase and, let's say, a potential to use the new flexibility resources, and, well, on the other hand, help us to reach the high system security also in future. On one hand, to take full advantage of existing network components, perhaps avoid or delay some investments by using the new flexibility, and of course providing some added value for the owner of these flexibility resources. And additionally, I just wanted to make a remark here that there is most likely in future need for other local, regional, non-frequency ancillary services, again, which would require taking the new features or the features of the new energy resources into use. So there has been always need for flexibility in the system since the very beginning of the power systems, since the very beginning of the transmission of the electrical power. But I just wanted to highlight here how we see the evolvement. So if we take a look at the, let's say, the ongoing trend, you could call it transformation of the electrical energy system or ongoing transition, it has obviously started already some time ago with the kind of an early stages of the wind integration. At the moment in Finland, we have roughly 2,500 megawatts of wind, and that has been integrated into the system during the last 10 years or so. The next stage, which I'm referring here more like a transformation of energy system, is due to the further increasing need to integrate wind and solar, the intermittent generation, into the system. At the same time, we see decreasing amounts of CHP generation, and also the sector integration and the electrification of the societies is something which ultimately should take us towards the ultimate target, which is rather often referred in the public word as a climate neutral power system. So if we look at the flexibility resources, the traditional approach before the start of the transition, the TSOs, the transmission system operators, we used to mainly use large power plants and really big consumption sites to provide the flexibility resources and kind of the mechanisms, the markets, places, market structures, which were kind of applied the channel to release the flexibility. Those were the well-known reserve markets, balancing power markets, and of course, from the network owner perspective, we can also invest to this kind of flexible assets, for example, dynamic compensation. So that was that has been the original flexibility toolbox. And as the wind integration started during the last 5-10 years, we have been using increasing amount of smaller power plants, smaller consumption sites, aggregated loads, and the demand side management. That has been essentially the concept which has been applied to channel the smaller resources to the reserve markets and balancing power markets. In parallel, we are working with the new balancing models. We are working with the new balancing periods, which should also help us to address these challenges brought on the table by the increasing amount of intermittent generation. But if we look at the next step, which really takes us to the topic of today, is that the transformation of the energy system, it brings into this electrical energy system huge amount of new flexibility resources thanks to the new energy technologies, energy resources. We are talking about energy communities, which consist of more traditional consumption equipment, but also these new battery energy storages, for example, electrical vehicles, heat storages, heat pumps, of course, intermittent generation as well. And on top of that, there is the topic of sector integration as well. And now the question is that how we can really take the full advantage of these. And of course, we will use the same mechanisms in some extent as always. We do our best to encourage these new resources to participate in the reserve markets, to the balancing power markets, to the intraday markets. But it's obvious that there is also the new added value through the potential of the new technologies. And that potential can be released by perhaps new market mechanisms, which are referred as a flexibility or this kind of locational markets, which are required to really address more the regional issues, more the congestion management related issues in the network. And of course, on the transmission technology side, there are also new solutions which we should use and apply. So just a brief look to the market structure. I just wanted to take this slide briefly here to highlight the fact that we have these existing products. We have the financial markets, we have the day ahead, we have the intraday, as well as the regulating power markets, the FRR markets, as well as the reserve markets. And regarding these, you heard already during the morning hours how the battery energy storages can contribute, provide some, let's say, new liquidity to those markets. But additionally, it seems that, again, we could take the advantage of the new technologies through these kind of locational flexibility markets, which could be the mechanisms using which we as a network operators could manage in future better, for example, the regional challenges and the congestion management challenges. But what is actually being meant by the locational needs, the congestion management needs? I thought that although the words, the terminology may be familiar to you, I was wondering if I should take a rather practical example here. So this is essentially a congestion management case in the network. And the traditional setup, which you can see on the left side of the screen, is a case where there is a region with some generation consumption. There are two tie lines, transmission lines, connecting the region to the grid. And for some reason, for example, because of maintenance, because of refurbishment of the line, we need to take it out of service. And traditionally, we have been able to manage the transfer, essentially to keep this line within its rated capacity, not to overstress the line, by making a separate commercial agreement, for example, with the owner of this generation plant, so that they would regulate their power so that the transmission on the remaining line would not violate those capabilities of the line to transmit currents and power. However, this setup is drastically changing already, and especially considering the coming years, because the CHP plants, the big single generation units, on certain regions, they are essentially phasing out and replaced by a renewable intermittent generation, which of course don't have the same kind of full control over the power generation. So here in the future scenario, of course, as a system operator, we have the same needs. We need to take the maintenance outages, we need to do the refurbishments, and we have still, under those circumstances, the obligation to maintain the system security, to keep the lights on this region. And for that, we need the same kind of a mechanism that the old single units provided for us. But now the tools will be different. Of course, the new renewable intermittent generation that provides us some flexibility. Essentially, when it's in generation, you can regulate the power down, but regulating the power up, that is more challenging. And for that, we need the demand side management of the existing consumption, but also we should take the full advantage out of the new flexibility energy resources, not being only the electrical vehicles, not being only the batteries, but also hopefully in the future, more and more, let's say, the measures coming through the sector integration, for example, the heat pumps, heat storages, which would allow us to regulate the power outputs and from the region over a longer period of times than those 15 minutes or 1 hour, which are essentially the regulation times in our balance markets and reserve markets nowadays. So just to summarize, I would say here, it's a bit long summary, but I hope I have still a few minutes. I would say that along with this ongoing transformation of the system, the new energy resources, they have a great potential to really play a key role in the management of transmission capacity, especially on the local regional level. But of course, if these features can be used on the regional level, then during those periods when let's say the flexibility is not required at local or regional level, it could be provided also, of course, on national level or even on the, let's say, for example, Nordic level purposes. But there are certain preconditions for releasing the potential, and here we are really entering the area where the R&D projects like you have here should, and we hope that it will provide the actual solutions, practical solutions, scalable solutions that will essentially in near future, hopefully already, increase the liquidity in our existing market forums, essentially the balancing power market, the reserve markets, but also the coming flexibility market venues. So, of course, we need the adequate power and the energy capability to address the network needs. We need something beyond the electrical vehicles, beyond the battery energy storages. But those are, of course, one pieces of the, let's say, the palettes, together with the demand side management and hopefully already in the near future, the measures coming through the sector integration. And of course, the aggregation will be one of the significant factors, combining different kind of sources with different power and energy capabilities. That is certainly one of the key features which will be required to address these issues. Of course, we need to have access to multilateral markets so that we can release the full value of the flex, so that the owner of the flexibility will get the best possible value out of their assets. And of course, this implies that there should be possibility to provide these services, not only for example, the local trader or the local retailer, but also for the grid operators, the transmission distribution system operators, and balance responsible parties, who at certain moments of the time has the greatest value of that kind of flex. And ultimately, of course, we need the technology solutions to facilitate the provision of flexibility. There's lots of focus in the development of technologies, but it should be also recalled that you can't release the value of the flex without having such interfaces, such exchange of information practices, such monitoring practices that will facilitate the participation of the existing markets, the new possible flexibility markets, and providing different kind of services for these for those who have the increasing need of flexibility, such as us as a transmission system operator, but also a wide variety of other electricity market industry players. So with these words, I think I will conclude my presentation, and I am most happy to answer any questions, comments, or remarks that you might have in your minds. Thank you very much.
Thank you, Tuomas. That was a lot of new information for me. And there is a question from Jonna. I think Jonna Kannosto. Do you want to present your question yourself, Jonna?
Yes, I can present it. So thanks, Thomas. This was very nice presentation. You was mentioned a 15 minutes balancing period. When this is going to be in use? I think it's at the moment, at least I haven't heard it would be in use.
Well, I can actually provide you a news flash directly from our websites. Just by accident, I had the news open here. So the latest from the 15 minutes balancing project is actually really an exact date. So it's the 22nd of May, 2023. And here in this news, you will also find some further details regarding the progress of the project. So this is the latest.
Okay, thanks. I will check that. And the kind of another question, is there a need for even a shorter time period than 15 minutes balancing?
That is an excellent question. I think there has been this kind of a visions and high level discussions that shorter balancing period might come in need. But obviously the time frame for the 15 minutes is already 3 years from now, and I think we need to put our focus to pull that one through, see how it works, and then what is required after that remains to be seen, I would say.
Thanks. It will be interesting to follow this development.
Indeed.
There is another question in the chat from Enzo Ikonen. So new flexible energy is to be distributed regionally more according to consumption.
New flexible energies to be distributed regionally. I would say that what I was describing regarding these regional needs, these are most likely more related to the rather short periods of time. Let's say it might be during a certain period of year, few hours every week during certain time when the system operators know that certain components might become overstressed. And of course, this would be added value beyond the value provided, or what would be available already in the balancing markets, on the reserve markets. But from the congestion management point of view, from the perspective to deal with the bottlenecks in regional networks, to balance the the possible overloading of the components, that would be a new feature, I would say. And again, it could be something that would provide another source of value for these assets. But whether this kind of regional balancing will become more and more typical, more and more often, that is, I have to say, that is something that remains to be seen. It depends very much how the distribution systems will in future plan their network, how they will operate their network. It will significantly depend how the balance responsible parties would like to use their assets or the flexibility asset to stay within their balance during, for example, this 15 minutes window. There is a wide variety of aspects which will certainly affect how these regional loads and consumption will behave in the future. So it will change. I think that's one thing for sure. But whether it will be follow more the consumption, I don't know. Perhaps I couldn't quite get the question. That might be my challenge here.
Okay, thanks. Thanks. That, I think, answered the question quite all right. Any other questions at this moment? Doesn't seem to be acutely at this moment. Okay, well, in that case, thank you, Tuomas. That was a very interesting and informative presentation. Lots of new information for me and lots of studying ahead. Then I think it's time to welcome Heikki Kurki to present the hybrid laboratory and what's in store there. Heikki, are you online?
Yes. Can you hear my voice?
Yes, I can hear you.
Okay. I share my presentation and screen next. Is it?
Yes.
Can you see it now?
Yes, we can see it now.
Okay. So I'm Heikki Kurki, principal lecturer in electrical engineering. I have been working for OUAS for several decades. I studied last century, but this year was a very special year as we moved, the whole university moved to the same campus as Oulu University has been since the 70s. And we have there new facilities, renovated facilities in the same big campus building as Oulu University has been working. And the new labs are located in the northern end of that campus. And this is the drawing of the lab department. It's in the first floor. We have total area of 1,100 square meters. And it was a big challenge to move here from the 10 kilometers apart, another campus where we were before. And we took some devices with us, but most of the equipment and networks, they are completely new, up-to-date, modern environment for learning and research. We have 4 different labs in this area, and they are mentioned in the picture. Energy lab, heating, ventilation, air conditioning lab, and then electrical engineering labs, and also automation and control labs in the same vicinity. And the energy is a common nominator for all these labs. Of course, we have also students in each of these degree programs, and the number of students is roughly 400. If we put together, they start every year 400 to 500 students in these programs. And this lab area, we call it hybrid laboratory. It combines these 4 laboratories. It is a learning and research environment for both universities, for the students, staff members, and our partners. And we teach and learn there the basics of each field of technology, but then especially emphasis is on energy, heat and power production, storing and distribution, and also loads there. Demand flexibility, as we have heard presentations on this field the whole morning, is one of the themes which are very important now. We have microgrid operation possibility there, energy efficiency and smart sensor systems. And also our objective is to operate it locally, but also remotely. Maintenance and security, safety issues are very important in this smart network environment. Demand flexibility, we just heard a very profound presentation about this. We know that electrical loads change and the weather-dependent power productions increase, and that the result is that energy production costs, they vary, and price per kilowatt hour fluctuates. And peak power moments also affect harmfully to the quality of supply, and that's why there is a need for demand flexibility. And smart network offers the means to implement it, and this we have done in the lab, and it's still under progress, and we are just building it, and it is divided into different projects which operate parallel or one after each other, depending on the projects. Smart electrical network combines production. We have there generators and solar cells. Now, and distribution and supply. We have connection to the campus 20 kV medium voltage network, and then also our local low voltage network. Storage of energy, which we have in batteries, electrical energy, and also capacitors are used for short time storage there. And of course, heat tanks are for heat energy there, but I'm focusing on the electrical network there, so I have put here only batteries. And then loads, we have all electrical devices combined to this smart electrical network, and lighting of the facilities in the first floor, it's part of that. Smart electrical network needs to be implemented sensoring, a lot of sensoring, metering, data transfer and analysis, and automation and control. It's a big project to build a laboratory with the resources which we have now, so it takes time. But let's see what we have done already and what are the goals in the future. We have had funding for first steps, and with that funding, we call it Sirius project. We have built and installed there the core elements of island and microgrid operation in the hybrid laboratory area. Pre-planning for this island operation possibility was done by Merus Power. And thanks for your presentation, Jonna. We got a good basis for the further development from you, your company. Contracting is going on, and it should be ready for manual operation by next summer. After that, we have plans to implement SCADA in that area and to make it possible to operate in microgrid. We have simulation tools. Oulu University is taking responsibility of building those tools. They make models for simulation. And then we also fulfill the minimum requirements for frequency containment reserve markets, which we heard there are different markets, but our reserve resource is a bit over than 100 kilowatts, which can be activated in 3 minutes after frequency step change. And that is not in our hands to participate the markets. We are just tenants in that campus, which is owned by Suomen yliopistokiinteistöt, Finnish university facilities, who own and manage all these nearly all university facilities in Finland. But we can model it, and we can make our simulations and also try it in practice in this limited area, hybrid labs. The demand flexibility elements are mentioned in the red boxes here. If you start in production, we have solar panels which are not indoors. They are on the roof, so they are not in this picture. Then we have generators. One of them is here, and the other one can be installed somewhere here. It should be smaller. Then there is a transformer which gives the link to the medium voltage network. This is the blue line here. 20 kV cables here. We have campus medium voltage network around us, and there is one transformer, and there is another transformer which can both feed this area after it is transformed to low voltage 400 kilovolt. And then we have switchgear and distribution panels. This is one of the most important for island operation. It combines the production and the loads in this area. And if now we don't have this switchgear yet, so the electricity is fed to this area directly from here, and we are just using the normal means of electricity feed now, but in the future we can use these other paths. Then we have also loads which can participate in the flexibility of consumption, smart lighting in this area, and also superheaters, water heaters, some motor drives here, and that makes all those components needed to simulate the situation of supply and demand balance here. So this area can be operating in island operation without contact to medium voltage network, but also in normal operation we feed our surplus production to the campus network. Solar cells are dimensions up to 60 kilowatt peak. This is not the only solar panel system on the roof of the campus. There are lots of other ones, but this is connected to the laboratory. Oulu University is taking care of the dimensioning, modeling, and procurement of the solar cell system. This is a schematic diagram where they should be in the future on the walls facing south and also on the roof. I'm not sure if this carousel or this round console can be done because there are some problems to fix it tightly to the roof. Inverters should be here in this part of the 4th floor, and we in the lab we are in the 1st floor. So the power is fed there. Generator, synchronous generator is up to apparent power of 50 kVA. And it works with supercapacitors when the switching to the diesel generator feeding is done. Energy storage batteries are dimensioned so that it is 40 kilowatts or 50 kilowatt hours storage. Then in the future, we hope to get also chargers and electric cars, which are one part of the reserve. This is schematic diagram of the distribution networks. Those components are all joined to this switchgear, which we see here. And then the normal use in the labs, we already use the feed from this direction here. And after this part is completed and we have the energy sources on the roof, etc., then we can use these energy sources to feed our laboratory distribution boards and all loads there. And then if there is more power than it is needed here, we have these batteries, or the power can be put back to SYK network, the owner of the facilities network. Two paths for this. Low voltage switchgear is the one of the is that combines all these loads, storages, and power supplies sources. Some flexible loads are mentioned here. We have a smart electric low voltage network. So this is one of the cabinets in the labs. There is a lot of metering. You know, the energy flow to each outlet from the sensors of these cabinets. The whole network is also modeled by the University of Oulu people and researchers there. We also get a power monitoring expert tool. This is Schneider product, and it gives the possibility to monitor all what happens there. There are different views and monitor pictures. This is not from our lab, but this is just to get an idea how we can control the whole distribution system inside the lab, and also storages which we have there. It needs a lot of information, sensors, metering, and we have Modbus network there where the metering is done. Then real-time network, and then IP network, Modbus IP network to SCADA. And this SCADA is to be purchased later, not in this project, but in the next project, perhaps in the year 21-22. And then we have real means to operate also in or simulate, at least in our facilities, the frequency control and demand flexibility situations. We get funding from EU. Don't ask me the sums, how much we have got. I'm not responsible of these economical things, but we are thankful for the funding. And we need also extra funding still to fulfill the benefits and to get use of the benefits which we have there. We offer also and invite partners who could participate the development of testing and implementing smart network components and elements, software and hardware, different concepts, new services, etc. A lot of bachelor students and also university master students and researchers can participate in these projects. So I hope that in a few months we can see and make demonstrations in these facilities. We are located in this part of the building, and in this bird's eye view, just the solar panel areas are shown here. But these three things and this part, the first floor is the place where we have this island network possibility. That was in brief what we are working on just now, and our plans for the future in this smart network area.
Thank you, Heikki. That was a very informative presentation and very interesting too. There aren't any questions in the chat currently. Does someone have a question in mind or comments?
Hello, this is Jonna. I could ask if the main target of the laboratory is to train the new experts or do the new development for the kind of smart electric grid system.
It's one of the main objectives. Of course, we have to environment to learn basics of each field of technology. But now we have the possibility to give the view to the future and also give some examples which way in our labs, which way the things are evolving right now. And also future experts, our fourth year students, many of them do now projects. We develop this laboratory environment. They have also they are doing studies on flexibility, demand flexibility, etc. Solar panel requirements, battery requirements, etc. And also monitoring and automation of the control of loads and of production. We have just started the work, and now they have the possibility during their studies to do some advanced studies in each of these fields. Smart network field. Okay, it's your word now, Sanna.
Yeah.
You can
Yes.
summarize the whole morning.
Yes, I was just about to jump in. Yes, thank you. Thank you.
Now stop sharing from here.
Yes, you can do that.
Hello?
Hello.
Okay, now you can hear me. It seems that I have double mute here. I was trying to. One more question, if there is a bit of a time.
There is time, yes.
Okay, very good. So you were mentioning that the demand side management is one of the focus areas. I was wondering, what is the approach that you are taking? I noticed that you're already participating or planning to participate the reserve markets. but considering, for example, the balancing power approach and essentially the scalability of these concepts, I was wondering if this demand side management development involves some kind of forecasting methods, how the load behaves, how much power and energy you can allocate, for example, during the next 15 minutes, during the next 1 hour, for flexibility purposes. Has this been somehow in the scope of your coming work, or could you somehow comment what is the approach that you are dealing with the demand side management aspects?
Yes, I focused during this in this presentation on the elements and the components which are needed, and with what we are doing right now. Yeah, and now, of course, it's possible only with the help of a lot of information from different sources. And of course, we put these elements and these ideas to different courses, and our aim is to give basic knowledge about the future energy markets and the challenges in electric production and transmission, and also load control for future electrical engineers.
Right.
And so that the world is changing from the static markets to the flexible markets, and they need new skills, new ideas. And now we have a laboratory where these elements are present, and we try to put them also in the different courses which we give to our students.
Okay, yes, that was exactly the point of the question, that now as you have established what you were presenting, what are the coming stages, and perhaps a small follow-up questions. You were referring to the amounts of data. So could you briefly describe what kind of a data you are collecting and how you're storing it, essentially what kind of a basis you will have in the near future to do this kind of a developments methods for doing the estimations and the prognosis, for example, of the available flexibility that you could provide for local or regional or even national purpose?
Now we have this power management expert tool, which collects data from all outlets and all cabinets which we have, so we know how much energy is used in this lab. We now have the possibility to collect all the data from in that area, hybrid lab area, and then also control, monitor it. It is monitoring tool, but not a part of the we can't operate. But the next step is to get a SCADA, and in that tool, we hope that we get also we can put together the information on the market, our own information, and demonstrate how the benefits can be realized for the partner on the frequency balancing market or power balancing markets. And that is the next step which we are going to take, and we have not yet made any purchases. We have had negotiations about the software and equipment which is needed for that, but that is next year we get more detailed planning on that before we can buy it from our suppliers.
Okay, very good. It's good to hear, and it sounds very good, and I'm looking really forward perhaps hearing from you in the future. And it's it will be, I would say, really interesting to see that as this kind of concepts and setups are being developed, different parts of the country and the world, how the data that is gathered, hopefully with a good resolution, good enough, obviously have number of very good measurement points, and hopefully we'll have a high resolution data both from time and accuracy wise. So it will be really interesting to see what kind of results using that data. We will see if we will get some glimpse actually how the future loads behave or the prosumers behave, and perhaps get better understanding how much flexibility they ultimately can provide for the use of the network operators and other market participants. Thank you.
Thanks a lot.
Okay, thank you. Thank you, Heikki and Tuomas and Jonna, for your presentations very much. It seems that flexibility and adaptability seem to be the keywords of the day, and as we go forward, there seems to be a lot of room for cooperation and RDI work to further develop these things. Now, if there's not anything acutely in the chat, I'll just check. No questions. The clock is 30 minutes over 10, and we have used up the time that we had for this webinar. And thank you very much. And if you have any questions or comments, or if you want to give feedback on this webinar or have ideas for possible cooperation, please don't hesitate to contact. You can email me, sanna.hiltunen@oamk.fi. And I hope I'll hear from Tuomas and Jonna soon again, and Heikki, I will be seeing around here at campus. So from my behalf, I wish you all a very good day, and thank you.
Thank you very much.
Bye.
Bye-bye.
Bye-bye.